Okay, so to clarify some things with the flow experiment, talk about, a little bit about how Bernoullis equation applies here. Have this picture. We have a uniform cylinder. We have a tube in the side of the cylinder. It's open, so water flows out. Okay? Now, a couple of parameters. Pressure is equal to the atmospheric pressure anywhere outside of this cylinder. Okay? So anywhere where there's not water, pressure is atmospheric pressure, and any place where the water is in contact with the atmosphere, the pressure is atmospheric. The depth is measured, let's just say arbitrarily, from the center of the tube up to the surface of the water. And water exits the tube at some velocity, falls to presumably a level surface, and its horizontal range is from the end of the tube to wherever it lands. And we've measured all those things with, in time. And we've got linear and quadratic models for horizontal range and for depth. Okay? So we know all that. Now, I want to talk about how Bernoullis equation applies when we consider points A, B, and C. Okay? So, the other thing, incidentally, this is water, right? Now, where do sharks live? In water. So they must be sharks.
Yeah.
Okay? So we got a shark's fin up here just to indicate this is water, right? And we got a fin here. Now this fin should be much smaller because much smaller sharks live in the tube. Okay? Because the tube is small. You get bigger sharks up here. Okay? Now, and usually when we drink water we don't detect them, but they're there. A little extra protein. Okay. Okay, well now, how does Bernoullis equation apply, right? So Bernoullis equation for points A and B. Okay? Well, let's see. We know that 1/2 rho v squared plus rho g y plus p is constant, right? Okay? Now, points A and B, the velocity is the same. Now, I don't mean velocity of, little convection currents and stuff like this. I mean the velocity with which the water is descending, right? So you might take B to be just, an infinitesimal fraction above the center of the tube, so it's moving at the same speed as this. But it really doesn't matter much because the velocity of the water transporting through the tube is so low, right? And you're squaring it. So that 1/2 rho v squared in any case is really tiny and really can be considered to be the same anyway. Okay? So that's pretty much unchanging. Thus, rho g y plus p is constant, right? Now, as you go from A to B, what's the one thing you know changes?
Altitude.
The altitude, right? That's the one thing that changes. So we can say that y decreases. Right? So as we expect, if we've been in swimming pools and stuff, we've experienced the fact that our ears feel it, so pressure increases. It must, because this sum has to be constant, and if y is decreasing, rho and g are both positive quantities, okay? So clearly rho g y is decreasing, that means p must increase by the same amount, okay? So did I use y or h when I first wrote this down?
Y.
Okay. Since I'm going to use y for the depth, okay, and since it's going to have two different values, it's going to be less clumsy if I use h instead of y, but that still is something you would naturally read as altitude, right? And that's the way it's often written. You could see it written either way. Okay, so I'm going to say that h decreases so that p increases, right? So what's the change in h? Well, the decrease in rho g h I don't want to say the decrease, I want to say the change. The change in rho g h is what? Well, how much does h change? From here to here, the change in h is? I'm sorry?
However, the depth of A minus the depth of B.
Okay. And if the depth is y, then how much is the change?
Y?
Y? No. Y is positive. From A to B, the change is negative, right?
So negative.
So, the change in rho g h is what's the change in rho g h? The change in h is delta h equals negative y, right? Okay? What follows that rho gh changes by negative rho gy. Okay?
Yeah.
Thus, your change in pressure is equal and opposite to the change in rho gh. That would be positive rho gy, right? Okay? So, if we know y, we have the expression for the pressure, right? I think I told you that if rho is measured in kilograms per cubic meter and g is measured in meters per second, then rho gy will be measured in newtons per square meter, whatever newtons are. Anybody know what newtons are?
Measurement of force.
Huh?
Measurement of force.
Yeah, it's a force measurement. It's about 1/4 pound. But it's your standard international unit of measure. SI unit, okay? So we're not going to get into the meanings of those units, but it's a standard unit of force. And you end up then, if you carry out the units of the calculation, you end up with units of force divided by area, which is what pressure is. Okay? So your delta P is this. And with the information I think I gave you in the problem, I think people are kind of asking about when you talk about pressure, this allows you to calculate it. Whether you know what to do with it or use it, you can calculate it, right? Okay? Well, then let's see what we do with that. Okay, so now we know the pressure here is equal to the pressure of the atmosphere plus rho gy, right?
Mm-hmm.
So let's go ahead and insert that information into our diagram. So up here, the pressure is P atmosphere at A, right?
Mm-hmm.
And now it's changed by plus rho gy, right?
Mm-hmm.
So now we can say pressure. It will say pressure at B is atmospheric plus rho gy, right? And we can just emphasize the fact that the pressure at A is pressure of the atmosphere. And at this altitude, I think I might have told you, it's very close to 100,000 newtons per square meter. Comes out about 25,000, it's more closer to 22,000 pounds per square meter. So, surface of that table, a little more than a square meter, so you probably have 30-some thousand pounds pressure from the air. Okay? Now, that's acting down, it's also acting up, so all it's doing is trying to compress the table, except now the bottom of the table is a little lower than the top, so there is a little more pressure in the bottom than the top, means there's a little more force on the bottom than the top. So why doesn't the table get up and float away? Well, there's not enough more force to overcome the gravitational force, right?
Mm-hmm.
Pulling thing down toward the center of the earth, okay? Okay, well, anyhow, there we have that, okay? Now let's compare what happens at point B with point C.